In this video, we're going to look at objects sitting on slopes and how to find the forces involved with them. So this question here, we have a 25 kilogram box sitting on a slope and it's not moving. If it's not moving, what assumptions can we make about this box? Well, right away we should realize if it's not moving, that means it's not accelerating, right? And if it's not accelerating, we know something very specific about this. We know F net is equal to mass times acceleration, and if the acceleration is going to be 0, that means the force is going to be 0. So we know the net force on this box has to be 0, right? No matter what. If it's not accelerating, the net force has to be 0. And that fact is going to help us figure out all the forces on this box. So to figure them out, let's start off by drawing a free body diagram. Remember, a free body diagram means it's not touching any surface. It's sort of off there by itself. What forces do we have involved? Well, first of all, we have our gravity force. Do we know the magnitude of that? Well, we do know the box is 25 kilograms, right? So we can just do 25 times 9.81. Let's assume it's on Earth. And that gives us a value of 245.25 newtons, okay? And the gravity force, of course, is pulling it down because, gravity pulls stuff straight down towards the center of the Earth. What other forces do we have here, though? Well, we have to have a normal force, right? Because it's sitting on a surface. And what direction is that normal force going to go? Well, remember, normal forces always act perpendicular to the surface. It's like pushing it off of the surface. So if this is the surface here, the normal force is going to be 90 degrees to that surface. So in this diagram here, in the free body diagram, it's going to be something like this direction, right? We have our normal force like that. And is that it? Are those the only two forces? Well, the object's not moving, and if I look at these two forces are both sort of pulling in this general direction. So if those were the only two forces, this object should be accelerating in this direction. So something must be missing. And the thing that's keeping it there, we should realize, is friction. What direction will friction act? Well, remember, friction opposes motion, and although this thing isn't moving, it wants to slide down the ramp this way, right? So friction is going to oppose that. It's going to be the opposite direction. So it's going to be directly up the ramp or parallel to the ramp, right? Okay, so we have two other forces other than the gravity force. And the thing that we're trying to do today is figure out the magnitude of those forces. What numbers can we put to those two forces? Any ideas? Well, first of all, we have to realize all of these forces have to cancel out. They all have to sum to 0. And what I mean by that is that the x components of those forces, so those components, the forces in the x direction, and the y direction have to cancel each other out, right? So before we go on, I'm going to take a copy of this, and we're going to look at it off to the side. I'm going to show you two different ways to do this, and you can sort of figure out which one's going to be easier. So again, in order for all the forces to cancel out, the x forces, the forces in the x direction, and the forces in the y direction have to be 0, right? That's how we would get the net force to be 0. Both of those have to be 0. So if we make up, y, and right, left, we can break up each of these forces into their components, right? So for example, we can break up the normal force into its x component and its y component, right? We can break up the force of friction into its x component and its y component, right? Now, can we find what any of those components are? It turns out we can make some assumptions based on this. Because we know that some of the forces in the x direction are 0, that means that this force here, this component here, and this component here have to be equal to each other, right? They have to cancel each other out. And we also know that this force here and this force here, they're both pulling up, right? If we put little arrows on those components, they're both pulling up. So they're going to oppose this force here. So these two forces combined have to equal this force. So we can actually do a little bit of algebra with that to figure out what the values of those forces are. But it's not the easiest thing in the world. There's actually an easier way to approach problems like this. And this is the reason why I made a copy of this. Because what if, instead of making x up, or x to the right and y up, what if we made our coordinates along the line of the ramp? So what happens if we make x this direction and y the perpendicular direction? Right? So it's like we've rotated our whole page by 15 degrees, right? Because the slope is 15 degrees. Well, if we do that, all the components in this direction will be in the x direction. All the components in this direction will be in the y direction. So then if we look at our free body diagram here, I'm going to just copy that over here, the x and the y. So this is the x direction, and this is the y direction. Notice how the force of friction is in line with the ramp. So it's the negative x direction, right? And the y direction is in line with the normal force because the normal force is perpendicular to the ramp. So in this case, if we look at it like this, the only force with components is going to be this gravitational force, right? And it's going to have a y component and an x component, right? And I'll put the little arrowheads on there to show the direction of each one of those components. So do you see that? This is actually much easier to analyze because, you know, we have an x component and a y component of just one of the vectors. We don't have to break up these two into components. And it should still work out because this force here and this force here have to balance each other out in the x direction, and this force here and this force here have to balance each other out in the y direction. So if we could find these two components, we've basically solved our problem because this one and this one have to be equal to each other and opposite, and this one have to be equal to each other and opposite. So the question is, can we find these components? Well, to find these components, we need to know the angle, right? So that we can use a little bit of trig to find out the two components. Because we know the length of this is 245.25. So what's that angle? So to figure out that angle, let's go back to our diagram here. We know that this angle down here is 15 degrees. If we have a perpendicular right there, that means that this angle in here is 90 degrees, right? And if we drop the vertical from there, because this is sort of to represent the gravity, the line of gravity, right, would be straight down, you can realize that this angle here has to be 90 minus 15, right? If this angle is 15, this angle down here is 90, this one would be 180 minus 15 minus 90, which is 75 degrees, right? That means this angle over here would have to be 90 minus 75, right? Because, you know, they add up to 90 degrees. There's a 90-degree angle here. So this angle here would also be 15 degrees. Basically, this is a little similar triangle as this one, or as our slope. So the difference between, or the angle between, the normal and straight down, or gravity, is always going to be the same angle as the slope itself. So this angle in here is going to be 15 degrees, right? So if that's 15 degrees, this is a 90-degree angle here. We can basically separate gravity into two components, right? So we have the force of gravity in the x direction. Remember, this is the x direction. And we have the force of gravity in the y direction, which is this one. Now, in this case, the hypotenuse here is 245.25, right? So the y direction is the one that's beside the 15 degrees. So that would be cosine, right? So it would be 245.25 cos 15 degrees. And the x component, right, is the sine, right? So that's going to be, 245.25 sine 15 degrees. So we can do both of these calculations. FGX 245.25 sine 15 gives us 63.48. We'll round these all to nice significant digits at the end. Newtons. And the y component is 245.25 cos 15, which is 236.89 newtons, right? So now we know the length of each one of these, right? It also makes sense that this one is shorter than this one. We drew it roughly to scale, so it does make sense. So now if we want to find the force of friction and the normal force, we have to remember the sum of the forces have to equal 0 in the x direction and in the y direction. So remember, if the sum of the forces in the x direction, the only two forces in the x direction are this component and the force of friction. So the x component and the force of friction have to cancel each other out. That means they have to be the same, right? So FGX and FF are the same. That means the force of friction is just going to be this value. And I'm going to round it to two significant figures, so 63 newtons. Same thing happens for the y components. The y components have to cancel each other out. So this force component must equal the normal force. So that's just going to equal 236.89. I'm going to round to two significant digits. So it's going to be 240 newtons. And there we have it. Well, I can also round this one to actually 250 newtons if I round this one as well to two significant figures. So there's our free body diagram. We now have the three forces here that are required to make this box stay where it is, right? Due to that gravity force. The gravity force is pulling it down. The normal force and the force of friction are basically keeping it where it is. So there's a special name for this, when all the forces cancel out and the sum of the forces equal to 0. And you'll see it at the bottom of the page here, equilibrium. Equilibrium means the sum of the forces in all directions is equal to 0. So that goes for x forces and y forces. There's one more definition, static equilibrium. And static means stationary. So it's one extra condition. The sum of the forces have to equal 0, but also the object has 0 speed. It's not moving anywhere. So in this case, the box is experiencing static equilibrium because it's the sum of the forces is 0 and it's still. Okay, let's go on to the next question. An 1,800 kilogram car sits on a slope. A rope is tied to the bumper, preventing it from rolling down the hill. Assume the rope is parallel to the slope. The first question, I didn't actually put the question here. It's draw A, F, B, D. Okay? So what I'm actually going to do is I'm going to pause the video here, or I'm going to ask you to pause the video here. I want you to come up with the free body diagram for this car. Notice in this question, it's a little bit different. I want you to assume the friction is negligible. So I'm going to assume no friction. So let's actually just draw a very quick sketch of this, and then I'll let you do the free body diagram. So here's our slope. Here's our car. I'm actually just going to draw a box, just to make it simpler. If you want to draw a car, draw a car. But basically, there is a rope holding this car. So it's basically pulling it up with a force, and we can call that force tension. And that's holding the bar from the box or the car from rolling down the hill. Okay, let's assume there's no friction though. So I want you to draw a free body diagram for this car. Pause the video here, try it, unpause when you're done to see the answer. So here we go. There's the answer. Simple calculations, just a little bit of trig. The normal force was 17.4 kilonewtons, and the tension force required to keep that car from rolling down the hill is 3.1 kilonewtons. Now, the next question asks, if we were to cut the rope, how fast would the car accelerate down the slope? Think about it. How does this free body diagram change if we cut the rope? So obviously, if we cut the rope, this tension force is going to go away. But does anything else change? Well, we know the gravity force isn't going to change, right? The car has the same mass. Does the normal force change? Well, if you think about it, we still have the same components of the gravitational force, right? We still have the y component and the x component. So the y component is going to remain the same, right? The normal force is going to remain the same because the car isn't lifting up off the ramp. It's still going down the ramp. So it's still going parallel to the ramp, which means the normal force and the gravity force, this part, are still going to balance each other out. But there's nothing now to balance out this 3.1 kilonewtons in the x direction. So that's going to become the new net force on the car, right? So the car is going to be pulled down and to the right by gravity, right? The x component of gravity. So the new free body diagram will look something like this. It's going to draw it quickly. It'll have a gravity force, right? That's still 17.7 kilonewtons, but it's going to have these two components that aren't balanced out anymore. The normal force is, so this is still 17.4 kilonewtons. But this force here, this 3.1 kilonewtons, there's nothing to balance that out. So that's still pulling the car down, and this is still 17.4 kilonewtons. That stays the same, right? So because this is an unbalanced force here, I'll do it in blue, this unbalanced force here, that's going to be the net force on the car because the other forces cancel each other out. So the net force is just that 3.1 kilonewtons, right? Oh, by the way, something I forgot to do in this question, I forgot to say what was positive. I forgot to give us that x is positive down the ramp and y is perpendicular to the ramp. We should always do that. You should always sort of label what your positive directions are. So anyways, the F net is this, so that means we can find the acceleration, because the acceleration is just going to be the net force over the mass, and in this case, the net force is 3,100 newtons, approximately, over 12 or 1,800 kilograms. So the acceleration of the car will be about 1.7 meters per second squared down the ramp. So there we go. Now you know how to find how fast an object would accelerate down the ramp. And a little thinking exercise for you is, what happens if this angle changes? So this was 10 degrees in this question, right? What happens if that angle gets bigger, right? What happens to these two components if that angle gets bigger? What will happen to this acceleration because of that if that angle gets bigger? I'll leave that up to you to think about.